Hi class. In this lecture video, what we're doing is we're moving into chapter 9 and we're going to talk about right triangles and trigonometry. So actually in this class and geometry, we're really only going to focus on right triangles. We won't touch too much in with trigonometry. All right, well this first video is covering section 9.1, which is called the Pythagorean Theorem and its converse. So we have two objectives in this lecture. First is we want to use the Pythagorean Theorem. It's a very simple theorem. And then the last thing we want to do is we want to use the converse of the Pythagorean theorem. Okay, so what is the Pythagorean theorem? So it just goes like this. If a triangle is a right triangle, so that means its largest angle is a 90-degree angle, then the sum of the squares of its lengths of the legs, so we have legs A and B here, is equal to the square of the length of the hypotenuse, which is C. So really what we're saying here is leg 1 squared plus leg 2 squared is equal to the hypotenuse squared. Or a much more common way to see the Pythagorean theorem is just by saying a squared plus b squared is equal to c squared. And all the c squared here is it's the length of the hypotenuse, which is the length opposite that 90-degree angle like this. All right, so what are some what we call Pythagorean triples? So a Pythagorean triple is a set of positive integers a, b, and c that satisfy the equation a squared plus b squared is equal to c squared. Notice from this equation that c must be the greatest number, the largest number, and below are some what we call common Pythagorean triples. So like 3, 4, 5 is a Pythagorean triple because 3 squared plus 4 squared is equal to 5 squared. So that would be 9 plus 16 does indeed equal 25. And all of these other triples, 5, 12, 13, 8, 15, 17, 7, 24, 25, all of these are Pythagorean triples. So there's actually an infinite number of Pythagorean triples, but these are the most common ones that we'll work with. All right, so let's do an example. So let's say find the length of the hypotenuse of this triangle ABC and check to see that the side lengths of ABC form a Pythagorean triple and explain why. All right, so use either given form of the Pythagorean theorem. So I will always use this a squared plus b squared is equal to c squared. So the leg 1 squared plus the leg 2 squared is equal to hypotenuse squared. This is 1, however, using that first form. So as I said, I'm going to stick with that a squared plus b squared is equal to c squared form. And this is going to be my leg 1. This will be my leg 2. And this right here, this unknown value is my hypotenuse. All right. So also here, this is the Pythagorean theorem where I replace the hypotenuse with x squared because it's the unknown. And then I've got the 21 squared plus 20 squared is equal to x squared. So I substitute 21 for A and 20 for B here, very simply. Square both sides, you get 441 plus 400. You add them together, you get 841. And now here, how would you solve for just x by itself? Well, to undo a square, you have to take the square root of both sides, and the square root of x squared gives you just x. And you get the square root of 841. Which if you plug in your calculator is actually just 29. So the length of the hypotenuse here is just 29. All right, so the length of the hypotenuse is 29. The side lengths 20, 21, and 29 form this Pythagorean triple because they're positive integers that satisfy this a squared plus b squared is equal to c squared. All right, or as you can see here, this is the same exact thing we just solved. So not only were all those other Pythagorean triples I gave you, all those other triples I gave you were Pythagorean triples, but so is in this other one, 20, 21, and 29. All right, let's do another one. All right, ignore this writing here for now. That'll come into play in a second. But let's find the value of x, this leg here, and write the answer in the simplest radical form. So the simplest radical form. All right, so notice here that x is a leg here. We know the hypotenuse in one of the other legs. So I'm going to use that a squared plus b squared is equal to c squared. Plugging in 8 squared plus x squared is equal to the hypotenuse squared, 20. Now square both of them. You get this. Subtract the 644 over, or excuse me, the 64 over, and you get x squared is equal to 336. Now you see where the other stuff comes in. To get rid of the square, you take the square root. Now you get x, this length of this leg is equal to the square root of 336. but I want it in the simplest radical form. Well, it turns out that you can write 336 as 16 times 21, and 16 is a perfect square, so the square root of 16 is just 4. So the length of this leg of this triangle is 4 times the square root of 21. And you would leave it just like that, as 21 is a prime number. Or excuse me, it's not a prime number. It just can't, it does not a perfect square. Forgive me. All right, this is not a Pythagorean triple because this number here, 4 times the square root of 21, is not a integer. All right, let's do application problem. All right, so this is talking about calculating placement of a wire. So a 50-foot supporting wire is to be attached to a 75-foot antenna. All right, so here's the 75-foot antenna. Right, because of surrounding buildings, sidewalks, and roadways, the wire must be anchored set 20 feet from the base. So here's 20 feet from the base of the antenna. How high from the base of the antenna must the wire be attached? So notice it's not going to go all the way up to the 75-foot power, all the way to the end. It's going to go some here. All right, and let's give an exact answer and a 1 decimal approximation. Well, you can see here I have a right triangle. I know the length of the hypotenuse, and I know the length of one leg. So I just got to use that Pythagorean theorem to find the length of this leg of this right triangle. All right, so a right triangle is formed using this Pythagorean theorem, so that a squared plus b squared is equal to c squared. Plug in the 20 for the a, x the unknown for the b, that length of this leg, is equal to 50 squared. Now square both sides. Get 400 plus x squared is equal to 2,500. Subtract the 400 over. Now what you're going to do is you're going to get x squared is equal to 2,100. To get rid of the square, we take the square root of both sides. You get x is equal to square root of 2,100. Now you just have to simplify this a little bit. All right, so I'm going to write this as 21 times 100. Well, I know 100 is 10 squared, so that comes out as 10. So this is the exact solution. X is equal to 10 times square root of 21. Or if you plug 10 times square root of 21 into your calculator, you will get 45.8. So that's how high this wire will go up onto the tower. All right. 2 other theorems, converse theorems here. All right. So first off, we know if the sum of the squares of the lengths of 2 sides of the triangle is equal to the length of the third side, then the triangle is a right triangle. So what we're saying here is if you ever have a squared plus b squared is equal to c squared, and you're unsure what this angle is, right? Well, it doesn't matter. If you have a squared plus b squared is equal to c squared, then the triangle will be a right triangle. That's all this is. All right, so let's talk about identifying a right triangle. So a triangle has side lengths 85, 84, and 13. Is the triangle a right triangle? And explain. Well, to determine whether you have a right triangle, we use the converse of the Pythagorean theorem and see whether the lengths form a Pythagorean triple. So use that a squared plus b squared is equal to c squared. Plugging in here, now the highest number has to be the hypotenuse. So you would get 13 squared plus 84 squared. Well, does that equal 85 squared? Well, solving it through, square all the values as is shown. So 13 squared gives me 169. 84 squared gets me 7,056. 85 squared gets me 7,225. Well, indeed, when you add these two numbers, they are equal. So since this is a true statement, we can say there that the triangle is definitely a right triangle. All right, 2 last theorems. So if the square of the length of the longest side, which is C of a triangle, is greater than the sum of the lengths of the other two, the squares of the lengths of the other 2 sides, so if you have c squared is greater than a squared plus b squared, then triangle ABC here is an obtuse triangle. So this angle right here, C, is greater than 90 degrees. And then you can kind of see the flip side here. If the square of the length of the longest side of the triangle is less than the sum of the squares of the lengths of the other 2 sides, then it's an acute triangle. So if this is still its longest side, if c squared is less than a squared plus b squared, well then triangle ABC here is an acute triangle. All right, let's do one example. So let's classify a triangle. So a triangle has side lengths 6, 11, and 14. Is it acute, obtuse, or right angle? Well, what you have to do is you have to compare c squared to a squared plus b squared. So I'm going to leave this part blank here because I don't know if it's going to be a greater than, a less than, and equals. So c squared, unknown, compared to a squared plus b squared. Well, the 14 will go here, and the 6 and the 11 will go here. So you take 14 squared, unsure, compared to 6 squared plus 11 squared. When you square all those values, you get the following. Now, when you add 36 to 121, you get 156. So we see that c squared here is greater than 156. Well, if c squared is greater than the sum of these squares, then what we can say is the triangle is an obtuse triangle.